finish up looking at the unit step function. That's the unit step function. However, for our purposes, we generally look at this form, unit step. And they use just a U. Your textbook uses a U. I use a script U to represent the unit step function, capital. If you're given a piecewise function, you can define it in terms of the unit step function. This is a two-piece function. Right? You're given your function of t naught, where t is between 0 and t1, and then f1, or f naught of t for 0 to t1, and then f1 of t beyond t1. You can write f of t that way. Keep that in mind. That's how we're going to be solving initial value problems with impulse driving functions or piecewise driving functions. Like your project. Number 2. There's the Laplace transform. So you have g of t times unit step function. It's Laplace transform e to the negative s tau times the Laplace transform of g of t plus tau. No, for g of t times u of t minus tau. Right, so if you come back up to here, you define f of t this way, it will give you this Laplace transform right here. Right, because remember, the Laplace transform is linear. So it'll be whatever the Laplace transform of that function is plus now that theorem that we just did. That can be extended, so if you have a 3-piece function, you can write it that way. And then also you have a natural extension if it's 4 pieces, 5 pieces, 6 pieces, so on and so forth. Here is your second shifting theorem. Which is actually very similar to that theorem. It's just generally it's more convenient to have it in this form. The second shifting theorem really is going to be used mostly for inverse Laplace transforms. And then we get into the initial value problems. There is a simpler method if your driving force is only 2 pieces. Right, you can follow this 4-step procedure. Right, step 1, just solve the initial value problem where your driving force is F naught. first piece. Compute new values, C0 and C1, right, where it's y0 of T1 and y prime naught of T1. Then you find the solution of the initial value problem, where your driving force is F1, and your initial value is now given by what you just calculated, C0 and C1. And then just write it in that form. Right, so step 1 is finding your solution y0 of t. Step 2 is finding your solution y1 of t, and then your total solution is obviously first piece is y0, second piece is y1. Instead of doing the whole Laplace transform thing. But that only works for a 2-piece. If it's more than 2 pieces, then you'll have to just take the Laplace transform straight up using the second shifting theorem and the other theorem. Otherwise, the process is exactly the same. Right? It's just now a different driving force we're transforming. So what does that tell us? First, we have to identify tau, which is just 1. So transform of this is e to the negative s times tau. Tau is 1, right? So e to the negative s times the transform of that. No, I'm sorry, not plus 1, minus 1. Right. G of t is t squared plus 1. We want the transform of g of t minus 1. So when you simplify, you should get t squared minus 2t plus 2. That's linear, right? So you just take the transform of each term individually. Transform of t squared. 2 factorial over s cubed, right? And at this point, you can use the table provided. Minus 2 times the transform of t. Well, transform of t is just 1 factorial over s squared. And then the transform of 2 times the transform of 1, which is 1 over s. There's your Laplace transform. Here we're given f of t. It's a piecewise function, and we want its transform. The first thing we want to do is write f of t in this form. F naught. Should be plus, right? Sure. Yeah. Plus F1 minus F naught, all times the unit step function, evaluated at t minus the cutoff point, which is 2. And what is that? T minus 1 times the transform, or times step function of t minus 2. Your transform of F would then be this transform. I already used the linearity property. For my own sanity, so I'm not writing out too many times, I just grouped the terms without the unit step function and the terms with the unit step function. Transform of 2t to a rest squared, right? Transform of 1, just 1 over s. Now the transform here would be e to the negative 2s times the transform of t minus 1 evaluated when t is t minus 2. Right, so replace t with t minus 2. T minus 3, that's what you get, right?
And you're doing that with t minus 2 as this.
Well, I think I did the, you know what I'm doing. Should be t plus tau, not t minus tau. That's my fault. Let's just make a slight change here. That should have been plus 1 there, which makes that plus 2t. I'm just going to make that plus. Okay. That's the only change that has to be made there. Which makes this now t plus 1. Which makes that get transformed.
So it's tt plus 1.
T becomes t plus 2. If we wanted to, we could write that. Right, combine your s squareds together, combine your s's together. So you can write that as 2 separate fractions. Don't if there's any advantage to that.
How did you get t plus 1 again?
Replace t up here with t plus 2.
Okay, so even though it's...
Right, so it's the step function of t minus tau. So whatever you're multiplying by that, the t gets replaced with t plus tau.
Okay, got it.
And that's the function that you're transforming.
Okay. If it were t plus tau,
Then your tau would be negative, right?
t minus.
Because it'd be t, because then that would be, if you have t plus, let's say t plus 1, u of t plus 1, that's u of t minus negative 1. Right, so your tau would be negative 1 in that case. Right, and that's important because that changes what your e is. Because it's e to the negative s tau. So if tau is negative 1, this would just be positive s.
So if tau were 1, t plus 1.
Well, then tau would be negative 1 in that case. You'd have u of t plus 1.
U of t plus 1, and then t minus 1 is still t minus 1, so it would just be negative 2.
So if this was u of t plus 1 instead, then t would be replaced with t minus 1. So it'd be t minus 1 minus 1, which becomes t minus 2.
Okay, yeah. Got it.
First, write f of t in terms of the unit step function. F naught plus negative 2t plus 1 minus 1. Times the unit step function at t minus 2. Plus, now, it'll be f2 minus f1. So 3t minus that negative 2t plus 1. 5t minus 1, right? That's, oh, yeah, okay. Times the unit step function at t minus 3. Right, again, it's t minus your breakpoint between the pieces. Plus f4 minus f3. T minus 1 minus that 3t. Times the step function at t minus 5. Transform of f then. Transform of 1 minus transform 2t times the step function, what was it, t minus 1? Is that what it was? No, t minus 2. Plus the transform, what do we have? 5t minus 1 times u of t minus 3 minus the transform two t plus 1 times the unit step function at t minus 5, right? U of t minus 5. Transform 1 is easy. Minus. Tau in that first case is 2, right? Since tau is 2, replace t with t minus 2. That's what we're now taking the transform of, right? 2t minus 4. Plus e to the negative 3s, tau is now 3. Replace t with t minus 3. No, t plus 3, sorry. Tau is positive 3, yeah. 5t plus 15 minus 1, 5t plus 14. Minus e to the negative 5s. Now replace t with t plus 5. 2t plus 11. All right, transform 2t minus 4. 2 over s squared minus 4 over s. Plus e to the negative 3s. 5 over s squared plus 14 over s. And then 2 over s squared plus 11 over s. There's the transform. Throw some trig in there. Start off the same way, right? Sine of t plus. Take that second function and subtract from it the first function. Times u of t minus pi over 2. Plus, now it's that last function, and then from it subtract second. And then that should be u of t minus pi. What was that first piece? Sine. go to plus. Sine, no arguments. What is the transform of sine of t?
Whatever s squared plus 1.
What was it?
Whatever s squared plus 1.
In that second transform, what is tau?
Negative pi over 2.
Not negative. Just positive. Remember, it's t minus tau for the step function.
Oh, yeah, yes.
Which means we now take the transform. Cosine of t plus pi over 2 minus 4 times the sine of t plus pi over 2. Time that second transform is pi, right? E to the negative pi s, times the transform 2 cosine of t plus pi plus 3 sine of t plus pi. That's a problem. What's the transform of cosine of t plus pi over 2? You could use the definition. Or trigonometries. Pi over 2, thankfully, is nice. Because you can use the cofunction identities on cosines on all of them. Cosine of pi over 2 minus theta is just sine of theta. and then use the even odd properties. Sine of negative t is just negative sine t. Cosine of negative t is cosine t. That takes care of that transform. And we can just rewrite that function now, which I'll do later. Now I have to deal with the other one. So I think I'm going to do it at once. It was what? Cosine t plus pi. Sorry, 2 times that. Plus, then was what? 3. Do some different color. No, we'll not change that color. So can you would. Plus 3. This is going to require the sum identities on cosine and sine. For cosine, we're going to get cosine t times cosine of pi minus sine t times sine pi. And then on sine of t plus pi will give us sine t cosine pi plus cosine t sine pi. What is cosine of pi?
1.
Other side.
Negative.
It's negative 1. What's sine of pi?
0.
Oh, that was nice. Oh, then this is going to be what? Minus 3 sine t, and then 0 again. That now takes care of that. One over s squared plus 1 plus e to the negative pi over 2s times this transform. Right? So take what's in that transform, replace it with those two. So we want negative sine t plus cosine will become negative sine. Minus 4 sine of t plus pi of 2, but that sine is just cosine of t, right? Right, now replace that second function, what we're taking the transform of. Replace the whole thing with what we just simplified, negative 2 cosine minus 3 sine. Those are all now easy transforms, right? Pay attention to this, and I think this will help you with number 2 in that project. You know what? I can factor out that negative too, right? Let's go ahead and factor out the -1. Transform of sine, 1 over s squared plus 1. And then cosine is s over s squared plus 1. Oh, you can factor out a negative from that second one too. And there's your Laplace transform. Good? Inverse Laplace transform. Well, look, can't you write this? Here's where we have to use the second shifting theorem. That e to the negative 2s is going to tell us that tau is 2. It's going to be unit step function at t minus 2 times the inverse transform of 1 over s squared we replace t with t minus 2. And if we go back up to this second shifting theorem and see what it says. Transform of step function t minus tau times g of t minus tau is e to the negative s tau times just the transform of g of t. And remember, I said all these theorems come in 2 parts, right? The transform, and then it's inverse transform. So you have to read that backwards. The inverse transform of e to the negative st times big G of s, which is what the inverse transform G of t is step function of t minus tau times G of t minus tau. What is the inverse transform of 1 over s squared?
T.
Replace that with t minus 2. That's your inverse transform. We could write this back in its piecewise form. Only going to be 2 pieces. First piece is 0. Zero, 2. Right now, remember, this t minus 2 had to be f1 minus f0. But we just said f0 is 0. All right, so what minus 0 is t minus 2? T minus 2. So generally speaking, when you're solving an initial varied problem, you do want to go to that piecewise form. If it's just asking for an inverse transform, you could just leave it in terms of your unit step function. Oh, joy. I'm going to break this down into separate parts. Because remember, the inverse transform is also linear, right? So what we really want to do is just take the inverse transform of each of those three pieces and then combine them. So let's call this 1. Inverse transform 1 over s squared is what?
T.
Just t, right? Inverse transform e to the negative s times 1 over s squared plus 2 over s. Second shifting theorem. What is tau in this case? U of t minus 1 times the inverse transform of 1 over s squared plus 2 over s, evaluated with t being replaced with t minus 1. One over s squared was t, right? What's 2 over s?
2.
T minus 1. So that's just going to be what? T minus 1 transform, or not transform, sorry, u of t minus 1?
Plus 1?
You're right, plus 1, right? Right there. Let's call this 3, the inverse transform. What was it? E to the negative 4s times 4 over s cubed plus 1 over s. Second shifting theorem. I have to say that slowly. Tau is 4. U of t minus 4 times the inverse transform, 4 over s cubed plus 1 over s, where you replace t with t minus 4. What's the transform of 4 over s cubed?
4t squared.
Is it? No. So I look at my table. Because the transform of t to the n is n factorial over s to the n plus 1, right? T squared means n is 2. So the transform of t squared would be 2 over s cubed. That's 4 over s cubed. So it's not t squared, it's not 4t squared, it's
8.
half of that. Right? Because you could write 4 over s cubed as 2 times 2 over s cubed. Now that 2 over s cubed is t squared. But that t has to be replaced with t minus 4. And what's 1 over s? Inverse. Just 1, right? We're going to have what? 2t squared minus 16t plus 33. 16 times 2, 32 plus 1. So our function h of t, which is the inverse transform of big H of s, is 1 minus 2 plus 3. I'm going to rewrite this. Because now we're going to go and write this as the piecewise function. How many pieces are there going to be? Three of them. What's the first piece? It's just t. Now remember the second one there, negative t minus 1, has to be f1 minus t. Right, so negative t minus 1 has to be f1 minus t. That means f1 what?
Negative.
Just negative 1. I'll worry about the intervals after I get my pieces. That third one, that 2t squared minus 16t plus 33, has to be f2 minus f1. We just said f1 is negative 1, right? So add 1 to that. That's your f2, right? 2t squared minus 16t plus 34. I'm sorry, I'm not adding 1. Should be subtracting 1. Because it's minus negative 1. You're subtracting negative 1 from both. No, you're adding negative 1 to both sides. That's right, so that shouldn't be 30, but that should be 32. Those damn negatives always get me. Now we set up the intervals. First interval. Generally speaking, we're always going to start at 0. Goes up to just 1, right? Second interval, we'll start back up at 1, goes up to 4. And then that final piece is greater than or equal to 4. That would have been the driving force, right? If, let's say, we solved the initial value problem and we got y of s equals that, that would have been your solution. With a driving force, a piecewise driving force. Or if this was the transform of the driving force, then that would have been the driving force. Again, probably be easier to tackle this in pieces. What's that inverse transform?
Q cosine 2 T.
I know. So that's the easiest one to work with. All right, now, 2. Of course. Shifting theorem. The second one, this is going to be u of t minus pi over 2 times the transform of 3s plus 1 over s squared plus 9, evaluated, t equals t minus pi over 2. I'm just going to put this and slide. The inverse transform of 3s plus 1 over f squared plus 9. That's actually not difficult. So we can write it that way, right? 3s over s squared plus 9. Isn't that 3 cosine of 3t? Oh, but t has to be replaced with t minus 2. So it's going to be 3 times t minus pi over 2. 3t minus 3 pi over 2. What about that 1 over s squared plus 9? Well, we need that to be a 3. Then that would just be sine of 3t, right? So then you just multiply that by a third. But again, t gets replaced with t minus pi over 2. Now that third transform. E to the minus pi s times s plus 1 over s squared plus 6s plus 10. U of t minus pi times the inverse transform, s plus 1 over s squared plus 6s plus 10, now evaluated when t is replaced with t minus pi. God. Complete the square. That's going to be what? S plus 3 squared, and then plus 1. Yes, of course it is. Oh, that's actually not too bad, though. I'm going to write that then as this. And then split them into two separate fractions. That is a first shifting theorem problem. It should be negative 3s, yes, except not st. Should be t. S over s squared plus 1 is just cosine. And replace t with t minus pi. Minus two sine of t minus pi. Because then you get essentially 1 over s squared plus 1, which is sine. And then replace t with t minus pi. So that'd be the third piece. Two cosine 2t minus, right, because that was a minus up there instead of a plus. The second piece. plus that third piece, right? Because that was a plus there. Oh, right. That t also should have been replaced with a t minus pi. That'd be negative 3t minus 3 pi. Or plus, right? Because there's a negative 3, see? That should be a plus 3 pi. Which I'll write as 3 pi minus 3t in the answer. Yeah, so what you could do now is use trig identities to simplify that. Right, so use your sum and difference identities. I'm too lazy to do that. Let me see if Wolfram does it for me. Okay. I'm also fairly certain your calculator would also simplify. Oh, wait, am I on the right account? Yes, I am. Good. What's today? 12? Does fully simplify it for me. That is a third cosine of 3t minus 3 sine of 3t. Why not let me copy as an image? Boy, going back and forth. Fine. I will win this war. I'm just going to put that there just so I don't have to keep flipping back and forth. And at the same time, so that's what that's going to simplify to. I'm also going to simplify the other one, and then I'll show you the code that I used. there's that second one. And there's what I used. I just used the full simplify command on each of them. Your calculator also does trig summifications, I believe. Actually, I know it does. I just forget the exact command. You may actually be able to just put in cosine of t minus pi minus 2 sine of t minus pi, and it should just simplify that automatically via enter. So I'm going to rewrite this. I'm going to put a plus because I'm also going to straight that negative through. I can't fit it. Actually, yes, I can if I move this whole thing over. There's your inverse transform. And if you were feeling really bold, you could try and write that as a piecewise function. Notice you most likely have to use trig identities to really simplify it, which is why I'm not going to bother, and I'm just going to say there's my answer. I'm happy with that. I'm done. So that one actually required both the second shifting theorem and the first shifting theorem. What was that? Bringing everything together. Questions so far? So I think what I'll do is I'll use that 3-step or 4-step procedure that was introduced to solve this one. I'll leave the other two for you. All right, the easiest way, for instance, to do this one, you have to just do the Laplace transform. Right, remember what transform of y double prime is, what transform of y is. And then when you do f of t, you're going to have to do it like we were doing previously. Up here, was it? Yeah. Where you write it as some difference of things involving the unit step function and then transforming it. And then obviously you'd have to then take the inverse transform using all the techniques that we've gone over. We don't have time if I want to do this in 5 minutes. Yeah, I should. First thing. All right, so step 1. Is to solve this. Except I'm going to add a little caveat, and I'll put knots down there. That is not a difficult initial very common solve. Let's just. Yeah, no, I'm just going to show it off. Let me show you how to do it on Wolfram. I think your calculator can also solve differential equations. I'm not sure if it can do IVPs. It should be able to. I don't see why it wouldn't be able to. D-solve. Now, it's y double prime of t plus y of t is equal to 1. So that's the equation. Now you also say, okay, well, it's going to be y0 equals 2, y prime of 0 equals negative 1. So that's your IVP in braces. Now you need to tell it what your dependent variable is, it's y of t, and what your independent variable is, t. There's your solution. 1 plus cosine of t minus sine of t. So that's y naught. Right, we'll just pretend that we solved that either using undetermined coefficients from before or the Laplace transform for the sake of time. There's y naught. Step 2, remember, is to get your C naught and C1. C naught was this. Y naught of tau, which is pi over 2 in this case. Cosine of pi over 2 is 0, sine of pi over 2 is 1. You get 1 minus 1, which is 0. C1 was y naught prime of tau. So that cosine is negative sine. Negative sine of pi over 2 is negative 1. That sine is going to be cosine, that's going to be 0. So that is minus 1. Step 3 is now to solve this. Y1 double prime plus Y1 equals your second piece, negative 1. Given these initial conditions. Y1 of 0 equals C naught, Y1 prime of 0, and I should put a 0 there, equals C1. No? No, sorry, it is supposed to be a tau, not 0. What should I do first? Right, so solve that. I'm again just going to use Wolfram. That isn't a very difficult one to solve. And I'll just copy and paste that. There's only a few things that I have to change, right? That becomes negative 1. This has to be pi over 2 equals 0. This becomes pi over 2. And we said that was also negative 1. That's cool. I didn't copy the whole D solve. There's your y1. -1 plus cosine plus sine. Step 4 is to write it back into piecewise form. Y of t is y naught, 1 plus cosine minus sine. Second piece is y1, and it's the same intervals. And there's your solution. So whether you want to do it that way or just straight up take the Laplace transform using unit step function, that's up to you. I wonder, I actually leave it for you as a challenge. See if you can naturally extend that 4-step process if it's more than a single jump. Right, so in other words, see if you can then go, okay, well then your third piece, you have to solve the y2 double prime. I'll do it here. Y2 double prime plus y2 equals that 0, the third piece, where your initial conditions are determined as we did before. Right, y1 of pi and y1 prime of pi. So do it both ways and see if that works. That's your challenge. Thursday's the last class. Everything's due. The third collection will be on Thursday. Again, I'll grade it while I take the exam so you can pick it up and take it home with you. The last group assignment is due Thursday before the class, and so is the last quiz. Exam number 3 is next class. It's 2 hours, 1 to 3. We'll start at 1 o'clock, and there won't be extra time granted. And so at 3 o'clock, regardless of when you get in, you're turning it in. And that's it. So only a few people didn't survive. I think we had 1 official dropout, 2 stopped showing up, and the other one that was an emergency, but that's not their fault. So 3 people didn't survive, it looks like. The rest of you did, congratulations. If you continue on the differential equation sequence, this was the easiest in the sequence. Partial's a lot harder than this. And nonlinear is even harder than that. Engineers, I think you should probably take partial differential equations. Because most of what you're working with will probably be partials, not ordinaries. I would argue that you probably should take nonlinear as well, because I don't think you're dealing with a lot of linear systems and linear equations. probably a lot of nonlinear stuff, but I'll let the engineers deal with that. What I'm going to do is just give you the rest of the class to do two things. Obviously, the worksheet on this stuff, and I did decide just to print out the review as well. Give you some class time to work on it. I'll just give everyone full credit. Turn it in. And then all those solutions will post at the end. So, how much time do we have left? What? 1 hour, 22, minus 8. So that'd be a total of 52 minutes.
So I have question 1, or I was looking at question 2 this morning. Was it going crazy? What is it?
Oh,
It
yeah,
was
you
what we
should
just
think
did today
you
in class.
What we did today?
Yeah, so I didn't know that, so I came here early and looked his office hours, and I was like,